Okay, scholars. I apologize for my appearance, first of all. It's 10:15 p.m. and this is the best you're going to get of me. So take it or leave it, I guess. All right, well, we do need to go over some important things. So I thought that I would just try to give you a lecture. Yay, I know you're very excited about that. This is an AP class. We're already behind in our schedule, so I just can't afford to miss another day. And I'm not the type who is just going to upload some YouTube video for you to watch or link some YouTube videos. So I thought I would make my own. So the topic of today is polarity and dipoles. And this just builds on what we have already been discussing regarding molecular geometry. So first, a reminder. And this is that covalent bonds may be classified as polar or nonpolar based on electronegativity differences. So, for example, I2, two iodine atoms stuck together, we would say that is a nonpolar covalent compound because these two iodine atoms will have the exact same electronegativity. They will be sharing the electrons evenly. There's not going to be any uneven sharing of the electron cloud. So we get no partial charges. The same can be said with carbon hydrogen, for example. I know this is not a complete molecule. I haven't satisfied the octet rule here. I'm just showing you pairs of atoms right now. That would be nonpolar. And so to make it very simple, and I'm not going to write this down because I've told it to you already, whenever you have identical atoms stuck together, or when you have carbon and hydrogen stuck together, we're going to consider those to be nonpolar substances. But something like hydrogen and fluorine, and this is an actual molecule, that would be polar. And let me remind you that we denote that with a lowercase delta to show partial charges. The negative, of course, on the fluorine, because fluorine is more electronegative than hydrogen. That indicates that this molecule has partially charged ends. So that should be a review. You should know all that already. Going on, I guess what I need to tell you now is that a molecule may be polar or nonpolar, depending not only on its bonds. So what we just got done discussing, if the pair of atoms results in a polar or nonpolar bond, not only on that, but also on its geometry, on its shape. And so here's an example. CF4, carbon tetrafluoride. First, I want to know, is this a polar molecule or not? Is the molecule as a whole polar? Does it have partially negative and positive ends, or does it not? And looking at this, you might predict that, well, this is carbon and fluorine. Those are different elements. It's not carbon hydrogen. So yeah, it must be polar. These are going to be polar bonds. And in that case, you would be correct. However, when we look at the molecule as a whole, it gets a little bit more complicated. So the best way for me to teach you this is with an example. This is what you will always do now. if you have a molecule and you need to figure out if it's polar or nonpolar. Step one is going to be drawing the Lewis structure and figuring out the molecular geometry. So all of this is just building off of what we've already discussed. So the Lewis structure is very clearly going to be like this. Blah, blah, blah. How are y'all this evening? I hope you guys are having some enjoyable asynchronous snow days. Although I don't think this newest round of snow got us any snow that we can pack and build snowmen and stuff out of, did it? Okay, so when I do the Lewis structure, it's going to look like this. And you guys should all recognize that this is AX4. It's got my central atom. Carbon has 1, 2, 3, 4 electron domains. I know right away it's going to be tetrahedral. And here's where this gets important. In order to answer this question, is it polar or not, I do need to now redraw the molecule, because I have got to think about its shape and how the shape affects all this polarity stuff. So a tetrahedral structure looks like this. If you're still confused about this, you can look up pictures online. I posted those dumb little pictures that I made. So you want to refer to those. Really make sure you understand the three-dimensional structure here. My wedge there showing that fluorine is coming out at me. The dashed wedge there showing that fluorine is going behind into the screen. I'm trying to draw this three-dimensionally. So what I'm going to do now is I'm going to draw what are called dipole arrows. These are arrows that are shaped like this, where the positive little tail of the arrow is on the less electronegative element, and the head of the arrow is pointing towards the more electronegative element. And you draw this on every pair of atoms where there is an electronegativity difference. I could have drawn these arrows up here in these examples. In this first example, I cannot even draw one because there is no electronegativity difference. Same thing here. There's no significant electronegativity difference for the carbon and the hydrogen. So I cannot even draw dipole arrows there, but I can draw one on the HF, and it would look like that. It is just it's a way of showing which way the electrons get pulled. It points towards the more electronegative element. And as a result of that, we get the partial charges. So whenever you have an arrow like this that is not canceled out by any other arrows, we would say that the molecule has a net dipole moment. You'll see this in a more complicated way in a few minutes. And that's what makes it polar. And for a linear molecule like HF, of course, there are no other arrows I could draw, and it's not canceled out by anything. It has a net motion to the right. That's the direction the electrons get pulled. So I'm going to draw a dipole arrow along every pair of atoms, along every bond. And you're going to see that, of course, fluorine is the more electronegative element. So there's my first dipole arrow between the carbon and the fluorine. I'm going to do that for every bond that I have here where there is an electronegativity difference. And this is kind of difficult to picture, so I do need you to try to think about the three-dimensional structure of this. You need to step back and look at these arrows and ask yourself, do they agree in any way to add together to something, or do they disagree? And by agreement, I mean, what direction do they point in? And so this arrow is pointing straight up, and these three are pointing partially downwards. So I have up-down cancellation. This arrow right here is pointing kind of out at me, while these two are pointing back behind. So there's back and forth cancellation. And then this arrow is pointing to the left. This arrow is pointing to the right. So there's left-right cancellation. I hope that makes sense. So this is where this gets tricky. I would say that this compound contains polar bonds. Like each bond here is polar because there is a difference in electronegativity between carbon and fluorine. But the molecule itself has no net, and that word net means total or overall, like what's left over. There's nothing left over if I add these arrows together. They cancel each other out. So the molecule itself has no net dipole moment. That's just a fancy way of saying that the dipole arrows all cancel. Therefore, it's a nonpolar molecule. You're going to be responsible for doing this, for analyzing molecules like this and telling me whether or not they are polar or nonpolar. And this is really the only skill that I need you to get today, Thursday. Tomorrow for me, today for y'all, I guess. Let's look at another example. How about CL3F? This one is quite tricky. Feel free to pause and see if you can get it. I'm going to skip ahead quite a bit just for sake of time. But when you do the Lewis structure, it's going to be tetrahedral. Carbon always goes in the middle if it can. I know it's going to be tetrahedral, so I'm going to try to draw it like that. You have got to redraw these according to the actual shape. I'm going to draw my dipole arrows. Chlorine is farther to the right on the periodic table, and typically that matters more for electronegativity. And so this looks exactly like the last one, where all of the arrows seem to cancel. Another way of thinking about this last example is that it's perfectly symmetrical. There's no asymmetry in the way my arrows are going or pointing. So of course they're going to cancel out. They're going to all disagree in terms of the direction they're pointing. I have this one pointing straight up, but these three point straight down. I have this one pointing out at me, but these two point behind, etc. Here, I have a similar case, but is it perfectly symmetrical? Think about that. And the answer is no. This dipole arrow that I've drawn right here, technically speaking, I should have drawn it as a larger arrow. What am I trying to represent with that larger arrow? I'm trying to show that this bond is more polar than the carbon-chlorine bonds. There's a larger electronegativity difference between carbon and fluorine compared to carbon and chlorine. Therefore, the carbon-fluorine bond is more polar. And so that's what I'm showing with the length of this arrow. The length of this arrow shows you like the strength of the dipole. How much are those electrons getting pulled up towards fluorine? And so while the arrows are pointing in the same way that they were in this last example, it's not the same situation. This is an asymmetrical situation. Fluorine is more electronegative. It's going to hog, pull the electrons up towards itself more than the chlorines will. And so I do have a net dipole moment. This molecule is polar. And so, so we would say something like this, based on what I just said, there is thus a net dipole moment pointing up to the fluorine. So fluorine is now going, and now that I have decided that, that there is a net dipole moment, that's a fancy way of saying, yeah, this is a polar molecule. And what do we have to do with polar molecules? We have got to show where the partial charges are. Where's the partial negative and where's the partial positive? I've got partial negative up here. And this really doesn't matter. It's really up to you. But I'm going to draw the partial positive kind of just down here somewhere. Some people like to stick it on the chlorine. Some people like to draw it closer to the carbon. It really does not matter. So look at this molecule, see if these arrows make sense, what I'm doing, why I'm doing it. The arrows are a tool for me to try to figure out if the whole molecule is polar, if there is a net dipole moment or not. Okay, let's keep going. Let's do some more examples. I'll give you all a moment to try this one. Really simple Lewis structure, really simple shape. You guys should all know this already. I need to now redraw it according to the shape. I can draw the lone pairs if I want to. I don't have to. Okay, so now I need to draw my dipole arrows, right? We all know that nitrogen is more electronegative than hydrogen. And look at those arrows. Do they agree or do they disagree? Well, remember, this is a three-dimensional shape, a three-dimensional structure. It's like a pyramid with nitrogen at the peak of the pyramid. And so all of these arrows point up. They all have an upward component pointing up towards the nitrogen, towards the tip of the pyramid. So yes, there's agreement. And so there is a net dipole moment with nitrogen as the net negative and the hydrogen end as the net positive. So yes, this is a polar molecule. I'm not writing it out because you should be able to kind of write it out on your own by now, or think it through at least. It's polar because the dipole arrows agree. They do not cancel. So there is a net dipole moment. Because it's polar, I have to draw the partial charges. All right. Remember, boron is one of those weird ones that is stable with just 6. This is a flat pyramid, right? This is trigonal. The shape of this is trigonal planar, not to be confused with trigonal pyramidal. Okay, this is flat. And these arrows completely disagree with each other. One way of thinking about this, if this is difficult for you to visualize, you can ask yourself, if these arrows start going off in the direction that they're pointing, are they ever going to hit each other? Are they ever going to intersect? The answer here is no. The answer here is yes, they're all going to hit at the top of the pyramid. I guess that rule kind of breaks down for this one. Shoot. Okay, well, I don't want to say anything that confuses you. Maybe just scratch that. I'm just trying to help you understand what I mean when I tell you to analyze the dipole arrows and see if they cancel. You draw the dipole arrow towards the more electronegative element along every bond, take a step back, look at them, and see if they agree or if they disagree. These completely disagree. This top one goes up and it goes up, the bottom two go down. So there's up-down disagreement. This one goes left, that one goes right. There's left-right disagreement. So there's no net dipole moment. There are polar bonds. Like, these bonds are considered polar. We would classify them as polar bonds, but the molecule as a whole is not polar. Okay, let's do a few more. This one I should not have to tell you guys at all. This is the tetrahedral family of bent. You guys all know that water is a bent molecule. Draw your dipole arrows. You guys all know the story for this one. And yes, it is polar. It has a net dipole moment. We all know that the oxygen end, oxygen is very electronegative. It's one of the top 3 electronegative elements: nitrogen, oxygen, fluorine. This is very electronegative. It is hoarding, hogging, pulling those electrons, and those dipole arrows agree, and that both have an upward component. So yes, this is polar. SF6, we did this molecule the other day. Sulfur is one of those weird ones that can experience an expanded valence. I'm just going to do this one quite quickly. I'm not drawing the lone pairs on the fluorines because I don't care about them. Remember, we call this one octahedral in shape. So I've kind of already drawn it like that as best I can. And this gets quite overwhelming to try to look at the arrows and figure out if they agree or disagree. But I hope you guys can see that these arrows completely disagree with each other. I have one going straight up, one going straight down. I have 2 going left and right into the screen. I have 2 going left and right coming out of the screen at me. So those all cancel out. This is perfectly symmetrical. So all of the arrows will cancel, and it's nonpolar. If you're going to get a polar molecule, there has to be some asymmetry about it. Like, look at water. Water has some asymmetry. It has the hydrogens on the bottom. There aren't any on the top to cancel those out. So it's polar. This thing is perfectly symmetrical, right? It doesn't matter which way you turn it, it's going to look the same. It's symmetrical, it's nonpolar. This thing was asymmetrical. It has 3 hydrogens on the bottom, but nothing on the top. So it's polar. So that's probably the simplest way I can boil this down for you. If you're having difficulty thinking about the arrows and whether or not they cancel, it does require you to like picture the shape 3-dimensionally. So you may want to spend some time today like Googling the different shapes or looking at the resources I've posted on the classroom to really familiarize yourself with the 3-dimensional shape. But yeah, the idea is if it's symmetrical, perfectly symmetrical, the dipole arrows will cancel and it will be nonpolar. Okay, let's look at some more complicated molecules. This molecule we looked at earlier, and I told you that they will often write the names of these carbon compounds, or excuse me, the formula of these carbon compounds in a way that is that suggests to you what the structure is like. So there's my Lewis dot structure. I guess you guys are going to freak out about these dots. I'll put them there. There's my Lewis dot structure for, this is acetic acid. It's called vinegar or acetic acid. And this is a bit complicated because how do we talk about the shape of this? Well, this is really important. You guys need to get this. The shape, the molecular geometry that we've been discussing, it always has to be based around a central atom. Where's my central atom in this molecule? I don't have one. So you have to break the molecule down into chunks, into components. So I'm going to look at like this chunk right here, and I'm going to call this carbon here a central atom. It's the central carbon of this region. And then I'm going to make another region over here where that carbon is central. And then I'm going to make a third region right here where that oxygen is kind of a central atom. So you're just looking at the atoms and you're looking at what they're bonded to, and you're considering them one region at a time. So let's look at this first carbon region here. I guess I'll keep my color coding. This carbon has 1, 2, 3, 4 electron domains. That's tetrahedral. So the molecule is going to be tetrahedral around that first carbon. What about the second carbon? How many electron domains do you see? I see 1, 2, 3. Remember, double bonds just count as one electron domain. That's trigonal planar. This oxygen here, it has 4 electron domains, but 2 of them are lone pairs. AX2E2, that's bent. Why do I care about this? Because I'm trying to figure out if this molecule is polar. I've got to figure out the shape of it first. For an extended molecule like this, you have to break it down into regions. Think about one central atom at a time. So now I'm going to redraw it. This gets a bit tricky. You're not going to have to do this on the AP exam, probably. Okay, so there's my tetrahedral carbon. Do you guys see that? It's tetrahedral. And then we said this one is trigonal planar. And then we said the oxygen is bent. So it would kind of look like this. And I hope that makes sense to everybody. So now I need to draw my dipole arrows. Remember, we do not draw them along carbon-hydrogen bonds. Carbon-hydrogen by just by rule, in fact, is not polar. The electronegativity difference is not large enough. Carbon-carbon, I can't even draw a dipole arrow there because they're identical. Carbon-oxygen. Carbon-oxygen, oxygen-hydrogen. And so what we end up with is something that looks like this. People always get nervous about this. They get freaked out about where they should draw the positives. And it really doesn't matter. Like this carbon is partially positive kind of from both of the oxygens. I don't need to draw that twice. As long as you have a partial positive, partial negative for every polar area on the molecule, that is fine. Now, I want you to notice how I did this. It is impossible for me to say whether or not this whole molecule is polar. That's a nonsensical question because the molecule has a whole region on the left-hand side that's nonpolar, and then it has some bits on the right-hand side and on the bottom that are polar. So we have to talk about this in terms of polar regions. And I would say that this molecule has 2 polar regions. The CO is a polar region, and the COH is another polar region. It's got 2 negatives, right? 2 partial negatives. And so with large carbon chain molecules like this, we cannot say if the entire molecule is polar. That question stops making any sense. In fact, we can't even talk about the shape of the entire molecule. Just exactly like we break it down into regions where we analyze one central atom at a time. That's what we do with the polarity as well. We analyze it in terms of regions. And so here I have a region where there's a net dipole moment. And so I would call that a polar region. Here I have another region where there is a net dipole moment. These arrows agree with each other. They're both pointing towards the oxygen. And so that would be another polar region. I hope that makes sense. Okay. I think those are all the important examples I need to go over with you. So here's the steps for this, for just figuring out if a molecule is polar or not. One, you need to draw the Lewis structure. Two, you need to determine the geometry, the molecular geometry, and you need to redraw it according to that geometry. Three, you need to draw dipole arrows if you can. Four, you need to evaluate if the dipole arrows agree or disagree. Five, determine if the molecule is thus polar or if it has polar regions. And finally, six, draw partial charges if necessary. Okay. Well, that's all I got. So you guys hopefully followed that. What you need to do now is just go back and finish all the homework that regards polarity, whether or not molecules are polar. So email me with any questions you've got. Look back over this stuff. I will share this document, I suppose, in the classroom. And I look forward to your emails. And I guess we'll chat on Friday, which is also an asynchronous day. I'll probably make another video. Take care.